So, good morning everybody. So, today we are going to discuss topic droplet and spray combustion. First of all, what is the rationale for studying droplet combustion? Typically, if you look at combustion per se, very rarely we come across gaseous combustion. And for most of the almost 90% plus application, it is liquid combustion. Now, as in the combustion course, we have studied that liquid or solid cannot react in that phase. The reaction happens only in the gaseous phase. Therefore, in order for the liquid to combust, let us say hydrocarbon, it has to be converted to gas. Now, that conversion process, essentially how is it done? It is actually the entire process of combustion happens in multiple steps. First step is vaporization. Okay. In this step, the liquid vaporizes into hydrocarbon or the fuel gas. Now, that process, let us say if for example, if both fuel and oxidizers are liquid like in cryogenic engines or rocket engines, then both of them have their own vaporization characteristics. But for other application, let us say in a gasoline engine or an aircraft engine, typically oxidizer is in gas, is in air, but liquid, the fuel is in liquid form. Now, fuel in being in liquid form also gives certain advantages. For example, it is easy to transport and it will not burn as its own, it will not diffuse out. So, in a smaller volume you can carry more fuel. That is why for the safety purpose as well as for transportation purpose, liquid fuel is much preferred over gaseous fuel. So, that is why most of the applications use liquid fuel. Now, but for the liquid to burn, as I said, it has to first convert into gas. So, first step is vaporization, and there is a characteristic time tau Rf is the characteristic time for vaporization. That is the time it takes for the liquid fuel to vaporize into gas, but that is not all. Even if it vaporizes into fuel vapor, it does not mean it is going to react, because unless in the molecular level there is a proper mixing between fuel and oxidizer, they are not going to react. So, therefore, the next important step is mixing. Okay. So, the characteristic time given there is tau m. So, this is the characteristic time between fuel and oxidizer ingredients to mix. Now, this process, particularly for most of the combustion system, this process is very important. Essentially, it is a fluid mechanics process, but it is not only fluid mechanics, it involves other transport phenomena like heat transfer, like mass transfer. So, all of them are together will take part in the mass diffusion process, all of them together will take part in the mixing process. Now, this process will ensure that we have a combustible mixture, and then the third one is the chemical reaction. This is something we have studied so far in this course, the chemical reaction. So, the characteristic time for chemical reaction is given by TCH, which is the characteristic time for chemical reaction. Now, if I look at these three processes, the overall time for combustion is the sum of these three, or let me just write it as TV, because I am talking about just one. The sum of these three is the overall characteristic time, that is the time it takes for the liquid fuel to come in, evaporate, mix and burn. So, the out of these three time scales, if you do an order of magnitude analysis, this is the fastest one. Chemical reaction time is very fast. So, therefore, for most of the practical purposes we consider infinitely fast chemistry, because the chemistry is so fast that it will happen instantaneously, but these two processes are slower processes. So, therefore, the overall dynamics of the system depends on these two processes, and they may be of the same order of magnitude. Out of the mixing is primarily is governed by diffusion, but molecular diffusion is a fairly slow process. So, therefore, in combustion system in order to improve mixing, what we do is we generate turbulence. So, essentially it is a turbulent driven mixing which takes place in the combustion driven combustion processes. So, therefore, it will be essentially a characteristic turbulence time as well. Vaporization time, on the other hand, is something that we are going to discuss now, which is the time it takes for the liquid droplet to evaporate into fuel vapor, because unless that happens the process cannot start. So, out of these three, in liquid combustion most important part is this, the vaporization characteristic time. Now, what the point is that why are we talking about these time scales? If you have studied emissions also, right? If you look at any combustion process, they happen in a particular volume, right. So, always the idea of a designer is to ensure that the entire combustion process is completed within this volume. So, the fuel comes in, oxidizer comes in, they mix, they burn, and then they go out. That entire thing has to be completed within this volume. Now, all these things have their own characteristic velocity. For example, droplets will come with certain velocity, fuel will come with certain velocity, air will come with certain velocity. So, if let us say L is the length of the combustor we are talking about, then L by T is the velocity. This with this velocity, if we do, it will be able to burn it properly, and this T is this characteristic time. Okay. So, therefore, rather overall time. Therefore, this characteristic time is important to ensure that we are designing a system in such a way that the entire process is completed within the combustion volume or in the combustion length. If we make it shorter than that, the combustion process will not be completed, will create more unburned hydrocarbon, more carbon monoxide, etc., because the process is not completed. On the other hand, if you make it longer, process will be completed, the possibility of having more NOx will increase, because we are having larger area for the post combustion zone. And secondly, particularly for aerospace applications, it is very important to make everything smaller for the weight. If you go for a larger combustor, if in a rocket or a gas turbine engine, that adds to the weight. Similarly, in the vehicles also, you have to have a smaller length of the combustor to reduce the weight. So, therefore, most of the combustion processes, optimization is such that the length that is required based on this characteristics time is the combustor length, and that is what it makes is important to study this process. Now, as I said that we will be focusing on this because this is fairly fast. This is a fluid mechanics problem, so we will be focusing primarily on this, but later on we will look at these two together, because they cannot happen in a sequential manner, because as the vaporization happens, that process is also enhanced by mixing, and because there will be heat transfer which causes the vaporization, and as the heat transfer happens, the mass transfer also happens simultaneously. So, therefore, the mixing takes place simultaneously as the vaporization occurs. So, therefore, they have to be in certain cases studied simultaneously. Now, coming back to then the vaporization, we will start with the simplest possible scenario, which is droplet. We will talk about droplet combustion. This process is primarily driven by vaporization. Let us say that we have a small tube, and on the top of it we have a porous plug, and we send fuel through it, and all around it there is air. So, if we light it, a flame will be created. Actually, no, not a porous plug, a droplet is made, we send the fuel in such a manner at a very slow rate that a droplet is created. Now, around this droplet, when it burns, a flame will be created like this. Okay. We can also do it in a porous sphere of given diameter, but we also can create a droplet. Particularly, I think Dr. Agrawal has shown you pictures of the microgravity combustion. There the droplet combustion is actually one of the best studies of droplet combustion is done in microgravity, because you can create perfectly spherical droplet, you can see perfectly spherical sphere. Otherwise, in the presence of gravity, the flame shape and the droplet shape will be skewed, because typically becomes elongated. So, therefore, if you do it in microgravity, so whatever we are discussing here essentially pertains to microgravity type of situations, because that brings out the fundamental physics. When you add the effect of gravity, the things will get skewed. So, now if I look at the combustion here, this is the flame. Let us say this is a porous sphere, as I said, of given diameter. Let us say the radius of this sphere is R L. Okay. So, therefore, the mass flow of the fuel that is coming out to the surface of this sphere will depend on the surface area, right, is proportional to the radius. So, this will be some constant times the radius of the sphere, okay. And this constant k prime is independent of the radius. Now, due to the natural convection effect, here you can see that the flame will not be spherically symmetric. Okay. That is why I said that in microgravity we can get spherically symmetric, otherwise we will not get spherically symmetric. So, another experiment can be that instead of this, we take a thin wire and we drip fuel over it. Of course, this wire should be such that it should not be conducting much of heat. So, typically a quartz wire is taken. So, it will not be conducting heat, and then we drip fuel over it, then a droplet is created here. Okay. And then if you burn it, we get a fairly spherical flame, but not completely spherical. Now, if we look at the diameter of this droplet, let us say initial diameter of the droplet was d naught, okay. And then at various instant of time, we take images, we can analyze it, we can estimate the size of the droplet or diameter of the droplet. So, if we do that, it is shown experimentally that we get a relationship like this. This is called d square law. Okay. This is the most fundamental law for droplet evaporation and droplet combustion, is d square law, and it is universally applicable. By the way, I am talking here about liquid combustion. It is applicable to any type of liquid. It has been shown nowadays that it is applicable to solid combustion as well. Let us say if you have solid particles like aluminum and all, spherical particle, if you burn and if you monitor the rate of decrease of the diameter, it also follows this law. So, it is a very fundamental law. So, here d naught is the initial diameter, this d is the instantaneous diameter at any instant, t is time and k is a constant, and this k is called evaporation constant. Okay. Again, this constant is independent of time, it depends on the type of fuel that we are using and the heat and other things. So, if I look at these two experiments, I have two constants k and k prime. These two constants are independent of each other, these two constants can be shown to be related to each other. So, that is what we are going to derive. We are going to derive a relationship between this k and k prime. Now, if another situation we can think of, that this droplet, if we increase the flow rate little bit, then gravity will come into effect. The mass of the droplet and the volume of droplet is going to increase. So, its weight is increasing. Beyond a particular point, the surface tension portions will not be strong enough to keep it attached to this wire, then it will come out and it will fall freely. Okay. So, that is a freely falling droplet. In that case also, if I look at it, then we will, if you do it in a microgravity, you will get a situation like this, where we have a droplet and spherical flame around it. Okay. This will be spherically symmetric. Okay. Now, let us say, going back to this expression, if this as the time progresses, this diameter is decreasing, right. So, in the limiting case, where it is completely evaporated, this diameter is 0, right. So, let us say if we say that the total time it takes for the entire droplet to evaporate is T b, then T b corresponds to when d is equal to 0. So, we can get T b is when d is equal to 0, and that is equal to d naught square by k, right. So, as I shown here, this is a constant, d naught is the initial diameter, for a particular case that is constant. So, we have a specific time T b when the entire droplet will evaporate, and that is this entire droplet is evaporated now. So, that is how we essentially estimate the evaporation time. and that is the most important parameter we want to know when we are doing the analysis in the spray combustion. So, now let us, as I said, that let us try to relate these two expressions. So, let me just clean this. We now have two expressions and then we try to find a relationship between the two. So, first is the mass flow rate m dot is k prime r l, and second is the d square law. Okay. These are the two expressions. These are not independent equations, like I said, one can be derived from other. So, now let us look at a scenario where we have a droplet. Okay. There is a liquid droplet, and let us say the at a particular instant the radius of this droplet is r. Then the rate at which the radius decreases is dr dt. This is the rate at which the evaporation is occurring and the radius is decreasing. So, at a particular instant time t, the surface area of this droplet is 4 pi r square, that is the overall surface area of the droplet. So, the droplet is evaporating from its surface, this is a surface area. So, what is the mass rate of evaporation? The rate at which because of the evaporation the mass is coming out in the vapor phase. So, that is the rate of mass rate at which the droplet is vaporizing is given by m dot. Okay. This will be what? It is from continuity equation rho a v, right. Now, here rho is the density of the liquid. So, let me call that rho L. Okay. Area is 4 pi r square. What is V? Is dr dt, the rate at which the diameter radius is shrinking, right, dr dt. Now, for this droplet, this is the rate at which the vapor is going out. So, then this will be the rate at which the mass of the droplet is decreasing with time. So, since it is decreasing, I put a negative sign here. Okay. So, this is the instantaneous mass rate at which the droplet is vaporizing. Okay. So, we get an expression like this. Going back to our d square law, k t. Here, let us differentiate this expression. Here d naught is constant, k is constant, d is a function of time, right. So, if you differentiate with respect to time, only d gets changed. So, d is the diameter, which is twice the radius, right. So, we can write this as minus 2 r d dt of 2 r is equal to k. Okay. So, if I all right. Therefore, dr dt from d square law is minus k by 8 r. Okay. So, this is the rate at which the radius is decreasing, and that is the surface velocity here. So, we can put this back into this equation. When we do that, we get m dot now. We have a negative sign here, a negative sign here, they will cancel off. Okay. So, we can simplify this now. All right. This is according to our previous expression k prime r, right. Therefore, we see that k prime is equal to pi by 2 rho L k, all right. So, we have shown the relationship between these two constants, right. As I said, these are not independent of each other. Now, we can have two situations. One is, if we do this experiment, like I was saying, the droplet burning in microgravity, it will be a steady state experiment. We can do it at a steady state, slowly it is evaporating. But if we are dropping it from the fuel from a quartz wire, see, we can have one droplet free falling and burning. So, that will be a steady state process, but one possibility will be that we are continuously supplying fuel to it and the droplet is burning at the tip of the wire. So, that is an unsteady process. So, this is steady state, this is unsteady. However, the instantaneous rate of burning for both these processes is going to be same. Therefore, this process also can be considered to be quasi steady, because instantaneously, if I look at a particular instant of time, like what we have done here, at that instant both of them are going to look exactly same. So, therefore, this process is called the unsteady process is also quasi steady. It is not purely steady, but at a particular instant it follows the steady state assumption. Therefore, this process is quasi steady, and the equivalence of these two, because this one is for a steady state and this one is for the unsteady combustion. So, the equivalence of these two essentially shows that it is a quasi steady process. Now, let us go back then. So, then we will not have to differentiate between the two, we can just do the steady state analysis and say that both is going to be same in both the cases. So, let us just now go back to the particular droplet combustion and now try to bring in some more physics into it. Let us see what happens in droplet combustion. We have a droplet of certain radius, let us say r b, and it is burning. So, we have a flame all around it. Okay, this is the flame. Now, this is the fuel droplet. Let us understand the underlying physics behind this process. We have a flame here. So, what is a flame? This is a high temperature region, the reaction is taking place. So, temperature here is high. Let us say the temperature is T f, the flame temperature. Okay. So, the droplet is at a lower temperature than the flame temperature. The result of that is heat transfer. So, we get heat transfer from flame to droplet. Okay. Now, because of this heat transfer, the heat is coming to the droplet, evaporation is taking place, because evaporation requires some additional energy. So, the evaporation is taking place, but the evaporated fuel vapor here then has to burn, and it will burn only in the flame front. On the flame it is going to burn. So, therefore, the mass that is evaporated diffuses to the flame front. So, we have diffusion of fuel vapor to flame front or flame. Okay. So, this is the physical process that takes place in a droplet burning, that we have evaporation which is continuously supplying fuel to the flame, and then the fuel is supplying heat back to the droplet. So, these two processes occur simultaneously. If any one of them is disrupted, the droplet will cease to evaporate. Okay. So, that is why if you create very large droplets, if it goes out of the combustion zone because of its own momentum, then once it crosses the combustion zone, you will not have the high heat transfer. That stops the evaporation. So, flame will not be there, droplet will come out as big droplets. So, also when the droplet strikes the wall, how can it strike the wall? Because it has high enough velocity that before this evaporation can take place, it goes out of the flame zone, and in that case it is not going to evaporate, it will remain as the fuel droplet. So, therefore, when we are designing the system, these are the things that we have to keep in mind. The droplet size should not be very large, then it will not burn. Okay. So, let us look at this case. In this case, let us say that this is the ambient which oxidizer, let us say this is temperature is given by T naught or T. So, the ambient temperature is T infinity, and in order for flame to be there, we require to have certain oxidizer concentration, right. So, let us say the concentration of oxidizer is Y0F or YOF, YO stands for oxidizer, or Y infinity stands for the upstream condition. So, this is a coupled process of heat and mass transfer then. So, if we have to understand this, we have to look at both of them together. So, before we do that, we have to define some of the properties which we will be using. One of the things that we have to be using here, of course, I think it has already been defined, but for the repetition sake I will do that. We have fuel which is a particular species, and we have a oxidizer which is a different species, and the reaction is taking place with the interaction of these two species. So, this is a multi-component gas mixture. So, we have to talk about multi-component gas mixture. Okay. Let us say Ni is the molar concentration of species I can be 1 to n anything, and I is the mole fraction of I. Then mole fraction is given by, right, this we have already seen. So, in combustion typically we work in terms of mass quantities, not the molar quantities. So, therefore, we have to represent this in terms of mass quantities. So, that is mass concentration, this is x. Mass concentration is typically given by density of a particular component, rho I, right. So, this is density of I, particular species or component I. Then mass fraction equal to Y I is rho I by rho, where rho I is the density of particular species and rho is the overall density of the mixture. So, rho is overall density of the mixture, and rho I is Ni times Wi, where Wi is the molecular mass of the component. Again, these are the terminology I think you have already gone through. So, just repeating them because I will be using them. So, with this then the mass fraction Y I which is appearing here is okay. As I said, Wi is the molecular weight of the species. So, this is equal to you can see from here, this is so that is the mass fraction is related into the mole fraction, where x is the mole fraction. Similarly, now we can define the mixture properties, all the properties of the thermophysical properties and thermochemical properties can be defined. So, the specific energy, internal energy is given like this, where E I is the specific internal energy of the particular species I, Y is the mass fraction, therefore, this is the overall for the mixture. Similarly, C P, C V, this is the gas constant for a particular species I, and the for the mixture this is the gas constant for the mixture. Okay. So, this is something that this terminologies we will be using, that is why I just listed them. Next, now let us look at the processes that are occurring. First thing, what is causing this evaporation to happen? This heat that is coming from the burning flame to the droplet is causing the evaporation to happen. So, this heat is essentially the energy. So, first we have to quantify this, that how much energy is coming to the droplet. So, we write the energy, we estimate the energy flux. Okay. So, this energy that is coming in heat transfer, we usually neglect radiation. Okay. So, there can be two modes, conduction and convection. Okay. So, let us look at both of them. So, this is let us say the flame, n is the normal, is the velocity vector, the flame front. Okay. So, first of all, energy or heat flux due to convection will be given by rho v dot n, then integral C p dt plus a constant. Sorry, this is enthalpy, right? C p integral C p dt is enthalpy plus a constant, right? So, essentially what it is? Enthalpy mass flow rate, right. So, the total enthalpy convection due to convection. So, this is the energy flux due to convection. Similarly, we have energy flux due to conduction. What law do we use to represent the conduction? Fourier's law. So, that will be from Fourier's law. This is equal to minus k dt dn, right. Therefore, the total energy flux that is coming to this droplet is the sum of these two. So, I can get now the total energy flux crossing a surface. It will be given in terms of q dot, that is the temporal variation, that is the rate, and we are talking about surface. So, surface area. So, the representation is double bar represents the spatial derivative surface area. So, this is essentially rate of heat transfer per unit surface area, per unit area. So, this is given by this, and see here, as this I just said, this is a continuity mass conservation, but the area is not appearing because that is taken to the left hand side to represent in terms of per unit area. Okay. So, then this is equal to rho this v dot n, I will just write in terms of the normal component of velocity v n. Okay. Then integral C p dt plus a constant minus k dt dn. Okay. And this term, if I write in terms of the differentials, this is nothing but this, right, is the first derivative in time, second derivative in space, that is what this is. Okay. So, this we have got an expression for the energy flux. Next, let us look at this process, mass flux. Okay. So, mass flux of any species. Mass flux also will be because of convection, there is going to be some mass flux, and because of diffusion there is going to be some mass flux. Like I said, this is a problem which is a combination of heat and mass transfer. So, heat transfer part we have done here, now let us look at the mass transfer part. So, mass transfer again, first of all there will be component from convection. So, convection term will be this, right. This is the convective term, because that is the rate of mass that is coming in because of convection, where the velocity is v dot n. So, by the way, I would like to point out here that if I look at the convection this way, the convective mass transfer, we should have the viscous effect also included, right. This will be because of the viscosity, there will be the effect on the mass transfer. However, in most of the combustion problems, the Reynolds number is very, very high. So, because of this high Reynolds number is the ratio of inertial and viscous forces. So, high Reynolds number means the viscous forces are much less compared to inertial forces. So, with respect to the initial effect, viscous effect can be neglected. That is why we are not bringing in the viscous term here, because it is much less compared to the inertial term. So, therefore, now convection, this is given like this. So, therefore, the mass flux because of convection is nothing but rho I is overall rho y I, right, overall density times the mass fraction, and v is v n, normal component of velocity, right. So, this is the mass flux due to convection. Similarly, we will have mass flux due to diffusion, and the mass flux due to diffusion follows Fick's law. So, we have to bring in Fick's law here. It says that the mass flux is given by rho d, okay, where this d I is the diffusion component for the IS species in the n component gas mixture. So, d I is the diffusion coefficient. Okay. So, now if I combine these two, the overall mass flux for a particular species, again flux represented by double dot, that is the per unit area. This overall mass flux is the sum of the viscous the diffusion minus the convective effect, that is the sum, algebraic sum of these two. So, this comes with a negative sign. Okay. So, this is the mass flux. I would like to point out here that this d I is the coefficient of diffusion of particular species I in the mixture. So, every species will have different value for it. So, that is why for every species we will have an expression like this to estimate the particular diffusion coefficient. Now, with this framework, now let us go and get the conservation equations. We got the terms, now let us bring in the conservation. Okay. So, next we talk about the conservation equation around the burning droplet, where now we will bring all of them together. So, this is now our droplet at a particular instant. Let us say the radius of this droplet is given by r s, and we have the flame here. Okay. So, the distance let us say of the flame from the droplet center is given by r, and let us say the thickness of the flame is delta r. Okay. So, this is the where the reaction is taking place, this is the direction of r. So, we will consider a spherico-symmetric and steady burning of a spherical droplets of radius r s. Okay. So, these are the assumption that we make, that the burning is symmetric and the burning rate is steady. So, now if I look at this flame, the heat flux, the external surface and the heat flux in the internal surface is, let us say, q dot double prime. So, external surface we can get by extending this, because this thickness is delta r plus higher order terms, right. We can write it like this, is the differential heat. So, this is where the heat is generated. So, first let us look at the overall mass continuity or mass conservation. According to continuity equation, m dot is constant, right. So, we have m dot mass flow rate is constant. What is the m value of m dot? Now, this we take any radius, this should be applicable, right. So, let us say if I look at this radius where the flame is located. So, therefore, the overall surface area, try to imagine the droplet is burning spherically. So, the entire surface area will be where the mass is going to the flame front. So, that is given by 4 pi r square, right. So, overall surface area is 4 pi r square. The density of the mixture, let us say, is rho, and the velocity, let us say, is v. This is the velocity at that location. Then this is equal to constant. So, we can take any location in the flame and this is what is going to be. Now, here this term rho v then can be written as m dot double prime, right. This is the mass flux. If we just divide it by area, it becomes rho v m dot double prime. So, what we have then, this expression, if I look at this expression, okay, this is the expression. Now, this is at any radius, therefore, at the surface of the droplet also it is applicable. So, at the surface the radius we know is r s. So, therefore, we have, because 4 pi is a constant. So, we can take it to the right hand side, it remains constant. So, this is the r s square m dot double prime is a constant, where r s represents the quantity at the surface of the droplet, and this s, by the way, sorry, this is not 2, this is s. This s represents the droplet surface, not the species. Species will be representing by I. Okay, the s represents the droplet surface. So, this is the mass conservation equation. Next, let us look at energy conservation. Considering the spherical droplet that we have shown here, or the sphere that we have shown here, this is heat transfer per unit volume. Okay, three bars represent per unit volume. So, this is the rate of volumetric heat generated by the chemical reaction. Okay. So, the combustion is taking place, that is generating this rate heat. So, that will be typically given in terms of volumetric rate generated. Now, through this shell where the reaction is taking place, there is a heat transfer. So, that can be estimated by, again, q double prime is the flux. So, if you multiply it by area, that gives us the overall value, the rate. So, if I multiply it by area, at this surface the area is, right, this is the area for this surface multiplied by this flux, and let us neglect the higher order terms. Okay. Then this is the heat flux at the outer surface of the shell. This is equal to what is coming in and what is generated inside, right. Some heat is coming to this surface and some is generated inside. So, what is coming in is this one, right. So, that is this is the heat that is coming to this internal surface here of the shell, and some heat is generated inside this shell, that is equal to where this is the volume of this shell and this is the volumetric heat generated, right. So, therefore, this is the total energy balance. Now, this can be simplified as okay. Now, let us simplify this and get a final expression. So, if I expand this, some of the terms get cancelled, then if you neglect the higher order terms, finally, what we will get is we get an expression like this. You can do it yourself later, I am not going to details. You get an expression like this. You can see here in this expression we have delta R, this you can neglect this, all right. Now, this delta R is the arbitrarily you have chosen some thickness of the flame or some domain in the flame. So, for a limiting case when delta R tends to 0, then it is the flame front. So, as we consider delta R tends to 0, you see that this term and this term will vanish. So, we will have only these two terms here. So, that will be now, if I look at this term by the way, let us look at this term, this is nothing but d dr of right. If you differentiate this, you will get this 2. So, this is the expression is equal to the right hand side remains 4 pi r square this. Okay. So far so good. Now, let us bring in, we have been talking about the heat flux q dot. We have already discussed that this term is the combination of convective heat transfer and conductive heat transfer. So, now let us bring in those expressions. Then we will get d dr of 4 pi r square rho v integral C p dt plus a constant minus k dt. Here n which in the previous expression was dn dt dn, n was the normal, here normal is the radial direction. So, that becomes dt dr. Okay. So, this is the convective heat flux, conductive heat flux. So, this q term I have replaced by this two. This is equal to the source term, which is the volumetric heat generated because of chemical reaction. Okay. Now, from continuity equation we know that this. Okay. So, if I put it back here, I will get m dot C p all right. So, this was the integral equation, we just take the differential form of that. This is the expression for the energy conservation. As you can see here, we have the heat generated because of chemical reaction, which appears as a source term, heat transfer because of convection and heat transfer because of conduction. So, you have the overall energy balance. Next, since we are talking about combustion, we have to have species conservation as well. So, you have done the mass and energy conservation, now let us look at species conservation. Which is very similar to, is essentially the mass transfer term. Okay. So, this is the mass transfer because of convection, this is the mass transfer because of diffusion, this two we have already derived before. Okay. But now, when we are talking about the mass balance, this 2 is equal to the rate at which this is diffusing or evaporating, right, because the mass is being generated, species mass is being generated because of the evaporation of this droplet. So, this is the diffusion or the flux of the mass, but it is generated here. So, there is a source term here, unlike the overall continuity where overall mass generation was 0, but now for every species it is being generated because of evaporation. So, therefore, there is a source term here, and that source term is equal to the rate of evaporation, the rate at which the mass is generated because of evaporation. So, the source term will be given here is equal to okay. This is the mass generated at the droplet because of droplet evaporation per unit volume multiplied by area gives the mass. Okay. So, this term here is the species production rate or destruction rate by means of chemical reaction. So, this will have n minus 1 independent equations, where n is the number of species, right. So, if there n is number of species, we can have ideally we can have n independent equation, but there is one equation which is sigma y I is equal to 1, right. So, that reduces the number of unknowns to n minus 1. Okay. So, you are supposed to have n for n species n equations, but because the sum of the mass fraction of all the species is equal to 1. So, we can replace one of the equation by that, and that reduces the number of unknowns. All right. So, one more thing that I would like to point out here, that this entire process is considered to be isobaric, and that I had discussed earlier, that most of the combustion processes are particularly hydrocarbon combustion processes are isobaric. Pressure does not have direct influence on the combustion process. So, we will consider this as isobaric process. So, the heat term, the heat generated because of reaction term, is a function of delta H and y I and temperature, okay, where I is going from 1 to n. So, it depends on enthalpy change and temperature and the species concentration. Now, so we have now this equation and this equation which we need to solve. So, for that these are, as you can see, these are non-linear differential equations. So, we need to have some boundary conditions to solve them. So, next let us look at the boundary conditions. We are considering the surface of the droplet, let us say. So, I am just taking a segment of it. RS is the radius of the droplet. On this side we have liquid, on the other side it has evaporated. So, we have gas, okay. And at the surface the evaporation takes place. So, we will get the boundary condition at two places. One is at the surface of the droplet, other is far field, far away from the droplet, that is at r tends to infinity. We will try to get boundary conditions at these those two places. This one is fairly simple, we had already defined this. At r equal to infinity, the temperature is the ambient temperature, which we had defined as T infinity, and the species concentration typically at far field we will have only oxidizer, only oxygen. So, this will be essentially just y over infinity, right. So, other species are not present here. So, that is the condition at the far field. At the boundary, however, there will be this boundary condition is little more involved. So, at the boundary let us see what will be the boundary condition. If I look at the boundary of this droplet, there must be flux continuity. At the boundary of the droplet or at the surface of the droplet. So, there should be first of all mass flux continuity at the surface. That is, if I look at any species, for any species the mass flux at the surface is given by the area I will explain what these terms are. This term I am given in terms of YIO 0. This is the concentration of the species I in the liquid phase. Okay. So, this is what is inside. So, that the fuel composition we know what chemical it is. So, therefore, this is the fraction. If it is a mixture, it will be certain value, if it is pure fluid, it will be certain value. So, typically most of the fuel are mixtures, right, that in the fuel Agarwal has talked about. There is a mixture of various fuels. So, for each of them we know the mass fraction. So, this represents the mass fraction of that particular fuel species in the liquid phase, and there cannot be any diffusion in the liquid phase. After that, when it comes out, this is in the gas phase. So, gas phase there is a convection and diffusion. So, that is at this site. So, it will be given by at the surface R. Similarly, we will have energy conservation at the surface or energy continuity at the surface, energy flux continuity. This is a mass flux continuity. Similarly, we will have energy flux continuity. Now, here the gas is bringing some energy from outside to the liquid, and liquid is also bringing some energy from inside. So, these two should be matched at the surface. So, let us see what is that. So, first let us look at the gas phase. This we have discussed convection, conduction. this is energy coming from the gas phase, and this is equal to the same for the liquid phase. At the surface. Okay. Now, the temperature gradient at the surface in the gas phase is given by this, right. This is the temperature gradient or the conduction at the gas phase. S plus represents just outside the liquid surface in the gas phase or somewhere here. So, this is equal to So, essentially what I am doing is I am rewriting this equation. So, this conductive term in the gas phase is equal to the convective term in the gas phase minus the convective term in the liquid phase minus the conductive term in the liquid phase. So, K s represents the heat conduction coefficient for the liquid phase. So, S minus is in this. So, this is S minus, this is S plus, okay, two sides of the surface or the boundary. Now, why I have written it like this is a reason for this. Look at this term here. What is this? This is the overall enthalpy. Yeah, this is the overall enthalpy at the liquid phase, overall enthalpy of the vapor phase. So, the difference between these two is the change in enthalpy required for evaporation or vaporization. So, therefore, this is nothing but latent heat of vaporization. Okay. So, therefore, this this expression we can write as K j equal to mass flux, the liquid surface, latent heat of vaporization. All right. So, this term, total term here, the latent heat of vaporization multiplied by mass flux is the heat needed to vaporize. So, if you look at the vaporization process, what happens in this case is that since every liquid has its own latent heat of vaporization. So, let us say liquid initially was at certain temperature, lower temperature, we supply heat, immediately it will not evaporate. First the temperature will go to the vaporization temperature, then in the vaporization temperature it will absorb this heat, this amount, and because of this absorption at the same temperature it will evaporate. Then the gas will be finally heated to the temperature. So, if I look at this one, this is the, this expression says that this is the heat that is absorbing for taking the liquid which was initial some temperature T L to the vaporization temperature T V, right. This is the heat that is required, and then certain more heat is supplied for evaporating this. So, that will give the evaporation, and then that from the evaporation temperature to final temperature the gas is heated. Okay. So, therefore, this will give the difference gives the total process in which the vaporization is taking place. And so, the left hand sum term here is the heat supplied to the gas gas phase in the interface by conduction is the heat needed for vaporization, and the heat supplied by conduction to the liquid phase from inside. Okay. So, let me just now draw the schematic of it. So, this is what happens. If I look at this and plot the temperature variation. So, far away from the surface, temperature is the initial the internal temperature T naught. Okay. Let us say this is T naught. This is the surface where the evaporation is taking place. So, far away from it, temperature remains constant as the internal temperature, but there is heat transfer to this surface from outside continuously. Because of that, the temperature starts to rise and then it reaches the surface temperature here. So, the surface temperature is different from the internal temperature, and here, so this gradient here is okay. So, K S dt dr S minus. Now, this term in the right hand side, this also you can get in terms of the other physical properties, because this is what is happening. The temperature initially far off from the center is far off from the surface remains the initial temperature of the liquid. Is, if you look at this, is very similar to the flame description, right. Now, in the classical theory of flame estimation, what do? We say there is a conduction from the flame to the unburned gases, which raises the temperature to the initial temperature to the flame front temperature. So, same thing is happening here. We have heat conduction to this inside that raises the temperature till it comes to the surface temperature. So, therefore, this process here, this change depends on what? It depends on this temperature, it depends on initial temperature and the heating value of the liquid fuel or the heat capacity of the liquid fuel, right, not heating value, sorry, heat capacity of the liquid fuel. So, this is equal to C L T s minus T naught, right. This is per unit mass flux. So, just multiplied by the mass flux. C L is the heat capacity of the liquid. This is the change in temperature going from T naught to T s multiplied by the mass flux is equal to nothing but the conductive heat flux. So, essentially what we are saying is that this conduction is bringing in this change in temperature, right. So, now then in this expression we can write this as this is equal to okay, where this m dot is same as this, right. This is the mass of fuel that is evaporated. So, because in this expression also the evaporated mass flow rate, this is evaporated mass flow rate. So, therefore, this is the expression. So, what is this term then? Now, previously we said that we have the heat of vaporization, latent vaporization. That represent that once you have taken it to the surface vaporization temperature, then the amount of additional heat you require to vaporize it. But like I was saying that liquid is initially at some other temperature. So, we require some energy or some heat to take it to the boiling temperature. So, that is this one. So, therefore, this term together is the heat needed to convert unit mass of liquid to vapor at a surface temperature T s. Okay. So, initial liquid was at temperature T naught, surface temperature is T s. So, this is the enthalpy required to take the liquid to the temperature T s, and then this is the energy required to convert that to vapor. Okay. So, now this term together I will just write as Q. Okay. Then get kg Q, all right. So, all right. So, this is the mass flux from the surface or the evaporated mass flux. Now, let us look at some specific cases. first let talk about pure evaporation, no combustion, only evaporation taking place. So, essentially what it means is that we put the liquid in a hot environment, okay? Then pure evaporation will take place. So, first let us talk about pure evaporation. We are still essentially gathering the ingredients to get the final, just 2 minutes, get the final formulation. So, first let's talk about pure vaporization. So, only fuel species that comes out of the liquid phase needs to be considered here. So, let F represents the fuel. Okay. So, going back to this expression, because this is the heat conducted from the hot environment to the liquid surface. Now, this term here Kg, what is this? This is coming from Fourier's law, right. So, conduction coefficient. So, that can be written as right. Now, let us assume that C g, K, etcetera are constant throughout the gas phase and represent some kind of average quantity. So, if we consider this to be constants, then we get, so let us assume that these are constants, we get if C g is constant, it can be taken in here. So, this is okay. C g is the heat capacity of the gas. So, we can write it like this. Let us define a non-dimensional temperature term B T. This is defined. So, B T is defined as C g T minus T infinity by Q. Q again is the heat required to convert per unit mass of liquid at a particular temperature to vapor. So, then this we define this temperature, this non-dimensional temperature like this, then we can write this, right. So, this is the energy flux boundary condition at the surface of the liquid. Similarly, we can have the mass flux boundary condition, which we have already discussed before. So, I will just write it here now. Right. This is the mass flux boundary condition. We can simplify this as okay. Here naught represents far field, this is the surface. Okay. So, far field mass flux is surface and diffusion, surface mass flux plus the diffusion term. So, that is what is coming here. Now, why I am writing it like this is, now we define another parameter, which is given by this. Oh, sorry, this O represents the interior, O represents the interior of this thing, and infinity represents the far field. So, the interior condition and far field condition, this is the surface condition. So, if I define it like this, it will be, I just wanted to show the similarity between the two. All right. Look at these two expressions. This is coming from energy, this is coming from mass transport. Okay. But if I look at these two expressions, they look very similar, they will be identical provided we have right. If we have these two conditions, then these two equations will be identical. Okay. So, let us stop here now and we will take a tea break. After that we will come back and discuss. The advantage of this is that we are reducing the number of equations. We are actually putting both the equations at the same form. So, we do not have to solve these two separately. We just solve one and the solution can be just put into the other. So, that is what is shown here, that these two equations are identical provided these conditions are met. So, next we will talk from this.